Welcome, everyone, to the EECS 370 discussion podcast. My name is Mason Nelson. I'll be your host. Joining me today is Sunny Nyack. He's one of our other IAs. So this asynchronous section of the EECS 370 discussion will be a weekly podcast with rotating staff that we'll send out every week after the last live discussion. The goal of this is to go a little bit more in depth to the concepts. We won't have the restrictions of the 50 minutes inside live discussions, but we'll still get through everything that will be covered in the regular discussions. So we'll start off with some logistics for the winter 2022 term. We are still under the University of Michigan COVID policy, so this doesn't really apply to the recordings, but if you go inside the classroom, please wear your mask at all times, do your responsible, be responsible. We do have options for remote work due to illness or other things. So just let us know what's going on. And moving on with discussion logistics specifically, we have a bunch of discussion sections this semester. And we don't really require discussion attendance, but I think they're really helpful. Any of the content taught in discussions is possible to show up on exams or homework. So I would definitely attend the discussions, but you can go to any discussion that you want. My teaching style, I think, is awesome, but if you don't think so, feel free to go to one of the other sections. We have a bunch of different teaching styles, a bunch of really awesome staff who know their stuff. So feel free to go to anything. And that's the same for the lectures also. Feel free to go to any lecture section. But this will be the asynchronous podcast style discussion that we'll release every week. We have a Google Drive that we'll be distributing most of our files through. This picture is from last year's Google Drive, but it's pretty much the same thing. We will link everything on the Google Drive from the website, discussion things, lecture things, homeworks, projects, and other admin items like the syllabus. So you can go to our website, which is eecs370.github.io, and check out all of those links to get where you need to go. Within each of those folders, we have a bunch of other resources, slide decks, worksheets, maybe some recordings. Just be sure to check out those folders for everything you might be looking for. A little bit about me. My name is Mason Nelson. My full name is Thomas Mason Nelson. So if you see that on Piazza, that's me. I go by my middle name. This is my 4th term being an IA for 370. I really love it. And so I mostly handle the discussions and the project auto graders in 370. So every week I edit the slides from the last semester. I'll be recording these discussions for you to watch. And then I make upgrades to our auto grader backend. So I know a lot about the projects. I'm a CS major. I'm minoring in math and Latin. And I've taken a couple of the upper level EECS courses, 482, which is operating systems, 484, which is databases, 373, which is embedded systems, 470, which is computer architecture, and right now I'm taking 483, which is compilers. So all of those except for 484 require 370. So I know a lot about the post 370 world if you ever have any questions. And I do a lot of other fun things here at Michigan. So just if you ever have any questions, hit me up. And now I'll let Sunny introduce himself. Talk a little about what he's done here at Michigan.
Yeah, hey everybody, I'm Sunny. I don't have a pretty slide like Mason does, but it is my 2nd term teaching EECS 370, and I'm really excited for the semester. As part of the 370 staff, I'm responsible for honor codes, as well as I do a bunch of small things. I work on the projects. Obviously, I'm helping out a little bit with the discussions and a lot of small things around the block, but I'm a CS major, also minoring in business. As far as upper levels that I've taken, I've just gone ahead and taken a bunch. So I've taken EECS 388, EECS 445, EECS 482, EECS 483, EECS 44, EECS 45, EECS 46. I'm taking EECS 491 right now. I'm also taking EECS 497 as an MDE. So those are all fun, really fun classes, and I'm not going to go through them individually, but if you do have any question about any of those, I'd be glad to answer any questions about them. I also do a bunch of fun stuff. I'm part of a couple organizations here on campus, including the Biomedical Engineering Honor Society, as well as a couple other honor societies and the Engineering Student Government. So, feel free to ask me about that too. So yeah, I'm just looking forward to hopefully meeting you guys all either virtually or in person. And I'm looking forward to a good semester.
Yeah, thanks, Sunny. We are looking forward to meeting all of you in person. We have office hours throughout the week. That again is on the EECS 370 website. So if you ever have any of those burning in-person questions, check out the website, see where our office hours are, and we'll see you then. Okay, so now we're going to get into some of the content. So today we'll talk about C, which is the coding language that we'll be using for the projects in this class. EECS 370 isn't really a coding class, it's more conceptual. We just use C to do our projects, to turn them into real things that we can use. But C is similar to C++, so that should be mostly reviewed from EECS 280. And then we'll talk about a bunch of different number systems, and including negative numbers on computers. So I'll turn it over to Sunny, who's going to talk about the differences between C and C++.
Yeah. So again, as Mason said, all the code in this class will be written in C. And so you can tell by the names C++ and C are going to be heavily related. C++ was developed after C. And so a lot of what the designers of C++ were trying to do in C++ was trying to inherit a lot of C, but also improve upon it. But C is really similar, but there's just kind of a layer of overhead. And I'll go into more of the specifics as we go forward. But a really good resource is this great website that you can check out. And it goes into a little more of the specifics than I have the time here to discuss. But if you're stuck on how to translate something that you traditionally would have written in C++ to C, you feel free to check that out. Chances are it's going to have your answer. But yeah, let's see. Mason, it looks like I can't move the slides forward, so I'll have to ask you for that. So big differences here. C++ has what they like to is very object oriented. And so they created this abstraction of classes and objects and structs. And when it comes down to it, all of these things are just managing memory, right? Everything when it comes down to it is just bits. And so the way C++ represents memory is in these storage. But in C, we only have structs. And so, later on, I will walk you through how to, maybe transition your understanding of classes to, using them in C. And so the way you work with these, with C+ memory in C++ is generally you tend to use operators such as new and delete. And new is responsible for, allocating memory, and delete is responsible for freeing memory. In C, we have similar functions. Malloc and free. Malloc is responsible. I like to think of it as malloc, memory alloc, and free is responsible for freeing memory. And if you look into the documentation, they'll be a little bit more different, a little bit different in terms of how you call them, but overall very similar. C++, we also have the standard string as part of the STL, but if you recall from 280, you should have been introduced to this idea. C++ strings are kind of just a wrapper to some extent around C strings. And C strings are similar to C++ strings, but they're just essentially arrays of characters. And at the end of this array, there's what we call a null terminator. And that null terminator, as the name implies, signifies the end of the string. But the functions that you're going to be working with these strings are also going to be different. For example, you can't use the equals operator on C strings without getting your desired behavior. And so I'll go more into that later. But you're going to be working with stuff such as like string compare and string copy as different functions for achieving the same goal. Also, in C++, as part of the STL, we had like different data structures such as vectors, sets, and maps. In C, those aren't standard. If I was in industry trying to work with those same things in C, there's other libraries you can include to get those implementations. But within the scope of this class, The only native group data structure is arrays, and within the scope of this class, this is all you're going to need. Also, a big change is working with output and input streams. In C++, we have cout and cin, as well as fstream to access files. In C, we have kind of their predecessors, which are printf and scanf. So printf is for obviously output, and scan is kind of a way to both parse output or input streams as well as parse any strings. So that's a really useful tool. And within C, before accessing a file stream, you have to use fopen, which essentially like creates a file or allocates a page to the file, and then fgets, which actually gets the content of the file. But again, you guys will learn a lot about this as you go. If this all looks very new, that's natural. But all right, let's move on.
Yeah, I really like this picture that we have on the left here. So like all these functions that we have in C on the right side of this little table, you could have used them in EECS 280, just we didn't because they're kind of old, and the STL is much more useful. But notice how C++ is almost a superset of everything that we can do in C, but there's this tiny sliver of stuff that we can do in C that we can't do in C++. Sunny, do you know anything that's in that tiny sliver?
There's a couple things that you can do with regards to like operators that just because of the arrangement of like C++ classes, if I were to try to overload a friend operator within the class, it would throw an error because it would interpret it as like a function. But there's ways to access I guess the best way to phrase it would be like predicted memory. Like if you think an object is going to take some certain amount of space in memory, you can aggressively steal it and then overwrite variables that you shouldn't be able to, which I've done once. But other than that, it's nothing that you're really ever going to need to use or want to use generally. So yeah, it's weird things.
Yeah. There is one thing I learned recently in 373 in C, just because, and we'll get into this as we get further into the course, but function arguments are handled differently in C versus C++. So technically you could declare a function in C with no input parameters, but whenever you call the function, you could add input parameters. Whenever you define the function, the actual code for the function, you can use those, but you don't have to do it in the declaration. So sometimes that makes things really tricky for 370 students because the function declaration doesn't match how it's being used, but it won't give you an error for that in C like it would in C++. C++ took that out because it does happen a lot that we mismatch our parameters, and C++ also adds overloading. So having different types of parameters to functions, but I just think that's kind of interesting. That's one thing that we do run into, but if you know how to use it, it can be really, really useful. So anyway, we'll keep moving on here.
Yeah. So throughout this class, we're going to use a bunch of data types. These are going to be the same data types that you've seen in other classes where you use C++. I'm not going to, I could go through that table. So chars are, single characters. They take a size of a singular byte. You're going to declare them with a singular tick mark as opposed to the double for strings. Shorts are called shorts generally because they're like half. I like to think of them as half the general int, which is almost always 4 bytes. And so shorts are going to be half that size. They're going to be 2 bytes. Ints, as well as floats, which is a single precision float, is going to take up 4 bytes. Doubles, I remember it by, it's double the length. It's a double precision floating point number, and that's going to take 8 bytes. And that's how you represent decimals and also really, really big numbers. Longs are going to be also, generally it's going to be double. They're called longs because they're supposed to be longer than your traditional integer, but it sort of depends on your architecture. So I'm sure that when you guys have been downloading programs, you've seen like versions where you've seen like a 64-bit operating system and a 32-bit operating system. And so all of that is determined by the actual architecture that you have in your computer. Most of you are going to be using 64-bit architectures. In fact, I'm skeptical that any of you are still using a 32-bit architecture.
Yeah, I think both Mac OS and Windows 11 require 64-bit now. So, man, 32-bit used to be a thing.
So if one of you are running, a Linux distribution that's still on a 32-bit computer, you might see a little bit different behavior. But generally speaking, 64-bit architectures, and we'll talk a little bit later in the course about what that exactly means. But they're going to have double the sizes for longs and pointers. And that might not make a ton of sense right now, but again, we'll talk about that later. Yeah.
All right. So I think now we're going to do a little bit of a code demo with some things.
Yeah. Let me go ahead and share my screen.
Awesome.
Let's see. Okay. So here I have little tutorial. It was put together by Maximus, another IIA for the class. And it's just kind of a walkthrough of some of the unique things about C or things that you might not expect about C that are a little bit different from C++. And so I threw together a visual debugger. I've personally only used GDB through the command line, so this is a little bit new to me. But before I go into anything, if you guys are struggling with projects at any point, I highly recommend learning how to use some form of debugger. So if you're using GDB, that's great. If you're using a Mac, you might be using LLDB, really similar, just a compatibility thing. But they're all support the debugger or the compiler that we use in this class, which is GNU. So yeah, I'm going to go ahead and walk you through a couple of things in here. So before I get started, here's an example of using and declaring and manipulating with structs. So a lot of you may have gotten used to using classes in 281 or 280. But in this class, we have to use structs because we're limited by the language C. Structs are really similar to classes, except unlike classes, everything is public. So if I were accessing a struct later on, and here's an example of a struct. I have 3 members. I have an integer member, I have a character member, and a double member, and these are the variable names. And so if I wanted to access an instance of this struct later, I would just access it by using .x or .y. You can still have functions that are members of structs, just like C++, but you're not going to have be able to create a new class or instantiate classes using the new keyword, among other things. So here's just an example of us declaring the type of a class. There's actually 2 ways to do this. So one way is listed here. And the way, I'm sure you can look at the syntax and figure it out to some extent, but here we're just, the type def keyword just kind of says that we're going to define a type of a struct, and then at the end I declare, the type, the name I want to give this struct. So then later I could instantiate a member using this. Another alternative that I personally use more is that I could declare a struct by just starting with the keyword and then following that with the name of my struct. And here I have the exact same members. But one thing that you can do, so if I was just trying to declare the struct, I would write that. But one cool thing that you can do using this notation is you can also instantiate or create variables of this type, such as instance, and that's nice in terms of syntactical sugar, but it's just a nice little thing that you can do. All right, let's see.
One thing I really like about the type def is that you don't have to type struct every time that you declare it later on. if you don't use the type def, I think you do have to type, like in this example, you'd have to type struct my struct and then the name of your variable. But with a type def, you could just use my struct, for example.
Yeah.
But I think that in most projects, our starter code will provide you good examples with that also.
Yeah. Second, I'm trying to figure out how to hide the Zoom screen sharing thing at the top because I can't actually. Yeah, I know, but I can't move my debugger forward. Let's see. I might just be able to squeeze this. Yeah.
Whoa.
Yeah, it looks a little wrong right now. Let me resize it. Does that look fine for you on your side?
Yep. Yeah, that looks good.
Awesome. So functions are going to be almost identical to C++. So you guys should be very familiar with this. All the same keywords apply. So you could have const functions, static functions. And yeah, so that should be what you guys have seen before. So I'm not going to spend too much time on that. So main, so obviously the main function of your program, which is what's going to execute when you compile your code, is going to be identical to the way C++ does it. So it can take two parameters. Those parameters aren't necessary, but they're going to be argc and argv. And so those are any command line arguments that you're specifying. And so you guys should be familiar with that from C++. So declaring variables, again, very similar to C++. One thing I do want to note, so in this first declaration that we have here, we declare a variable x. Whenever you declare a variable without, assigning it to something, without initializing it, that's what it's called. It's going to take whatever value was sitting in memory. So it's going to choose a random, in case of int, it's 4 bytes in memory, and it's going to say, these 4 bytes belong to this variable. Well, it's not going to assign any value. So if I ran a program earlier and it was filled with a random number, in this case, it's 32,759, which you can see over here on the left in terms of my local variables. That whatever value was sitting in memory is the value it takes. And so if you guys are using a Mac in this class, Macs do this thing called sandboxing, and it's a security thing. But basically, a lot of the time when your computer requests memory from the operating system, it will zero everything out. And so a lot of people have developed this practice where they declare variables and they assume that they're 0 to begin. But this isn't true across devices. And so if you guys were on a Mac and for whatever reason you're getting like behavior on your computer that appears to work, and then you go run on the autograder and seg faulting, a very real possibility is that you're assuming that the value is 0 and it's working locally, but it's not working on the autograder, which is running Linux. So it's really important to declare or to initialize your variables before you actually end up using them. And so, yeah, so here we have an example of, declaring, initializing a variable y. We assign it to 5, and you can see our local variables assigned to 5. And so here's our first instance of the difference in printing. I'll go into this a little bit more, but you'll notice that it's a lot different from cout, which you've seen in C++. And so in C++, if I wanted to print this variable y, I could print what I have right here, which is, standard cout, and then I just pipe it using the extraction operators. In C, we don't have the stl, so we don't have cout. And so the way we access the print buffer is a function called printf. It's really simple just to print a normal string. But if I wanted to, insert a variable into a string, it's a little bit different. And the way that I specify how to add that variable is I use something called a type specifier. And so there's a number of type specifiers. In this first example on line 43, right here, we have the D specifier. And D specifies a decimal number. Or actually, no, it's a integer number. And so if I want to print the number 5, I would put the type specifier, which is D, and then maybe any other thing. So I want to print a new line after that number. And then I can have my variable as another argument. And so if I had multiple type specifiers, we'll see in just a second, I could have multiple variables as the parameter. So here we declare a double, and a double is double precision floating point number. And so the way I print any sort of floating point number is I have this specifier, which is an F. You can see the entire list right here. And so I can very similarly, if I walk my plane forward, I can assign the value to Z, and I can print that to the output stream. So then I have an example right after it of us printing both, printing with multiple arguments. So we have two variables, Z and Y at this point, as well as X, but X is uninitialized. And we want to print them both in one line. And so the way we do that is we have multiple type specifiers, and then we just have multiple arguments in the order that they come in the string. So Z corresponds to the first type specifier, which is F, and Y corresponds to the second type specifier. All right.
One comment real quick. Yeah, you see that type specifier for %s. I would say we're about to show an example of that, but generally you probably don't need that since that formatted string, the first argument to the printf, can be just a regular string also. So you could just do printf with the string and only have that one constant string argument, but we'll show an example of doing it with the specifier here.
Right. So if I wanted, I could just, so here we have declare a variable called name. And for that name, we assign it to a value. And in this case, it's Maximus. And if I wanted to print out that name, I actually have two options, right? If I just wanted to print out the name, no new line character, I could print a %s, which is the string type specifier, and then the name, or I could just print name. And the reason for that is because this is actually just a string. And so if they're the same type, we achieve the same goal. But one thing you might notice, I kind of skimmed over it, is that we are using a C style string. So instead of it being your STL standard string, we declare it with a character pointer. And the reason that is the way we think of a C string is it's a pointer to a character, and that C string continues until we hit a null character. And so it's really just kind of an array of characters followed by a null terminator. And so, yeah, there's an example of us printing that name followed by a new line character. So next we have an example of us, like maybe I'm curious about how big, this name is. So if I look at how long Maximus's name is, it's 7 characters, right? And so each character is supposed to be 1 byte. And so maybe we might think that the size of the name would be 7 bytes, which you'll find that it's actually going to give us 8. And the reason for that is going back to the difference between C style strings and C++ STL strings is that we have the null terminator at the end. And the null terminator contributes to the size. So if I wanted to allocate enough memory to represent Maximus's name, I would have to allocate 8 bytes of memory because I also need to account for that extra new line character at the end. And this is really important, as you'll see later, for when I'm kind of declaring, let's say, arrays in that I want to load different types of names into. So yeah. So you can actually allocate more memory than you need for a string. It's considered to be done once I hit that null terminator. All right. So looping and if expressions, this is going to be exactly the same as C++. You will not be able to use, if you're used to using range-based iterators or just anything with iterators in C++, you can't do that in C. So you'll actually have to index. But other than that, these should be the exact same as what you've seen in C++. So here our example is just going to print positive, right? Because 3 is a positive value. Arrays, again, they're going to be treated the exact same that you've seen in C++. The only restriction that they're going to have is that, as I mentioned earlier, you don't have vectors. And so everything, as you should remember from 280, you have to declare an array at compile time, unless you, of course, want to make it dynamic. Throughout the course of this class, you don't actually necessarily need to work with a ton of dynamic memory. And then the reason for that, I'll get into later, is that we don't care about optimization for this class whatsoever. And so if at any point in this class, you're like, man, I need enough memory to store 30 numbers, but there's a chance I only need to store 5. Go ahead and allocate enough memory to store 30 numbers. And it's fine if you waste 25 other spots. So here I have an example of declaring an integer array of 5. So I'm going to have 5 sequential integers, and I can initialize them by passing this initializer list. And so it's going to take the values of 100, 200, 300, and 400. And so if I iterate through this list, I can do so by indexing, right? I can print out the values in order. Go ahead and do that. So it's going to do this a couple times, exactly 5 times. And then once it reaches the value of 5, it's going to break out of the for loop. All right. So now we're going to talk a little bit about, I mentioned strings a little earlier, and now we're going to talk about how to manipulate them, right? So the STL provides a lot of abstractions that C strings do not, because C strings are fundamentally just a pointer to a character. And so one example is the equals equals operator that the STL provides. When I do equals equals in C++ between 2 strings, so for this example, I have Maximos's name twice. And if I did an equals equals operator in C++, we would expect it to print true because they have the same characters. But in C, what actually happens is we compare the pointers or the addresses at where the strings are stored. And if we're comparing 2 different addresses, they're obviously allocated to 2 different parts of memory. And so every time this is going to return false, right? And so we need like an alternative for how to check if 2 strings are equals. And so the function that we have for this is called string compare or strcomp. And so we use it right here. And so the way it works is it takes 2 arguments, it takes both of the strings that you want to compare, and it returns one of 3 things. It turns 0, which is primarily is going to be your primary use for it, if the strings are equals, and then it's going to return -1 or +1, depending on the lexicographical ordering of these strings. And so if you're interested in like how lexicographical ordering works, I suggest you check out some resources from 280 or just Google it. But the primary use of this is going to be using to check for equality using the equals, checking if it's 0. So if I run this, I will print that they're the same name. Awesome. So now another thing that C++ allows us to do with their strings is they allow us to copy strings really easily. If I want to, assign one C string to another C string, I would use like the equals operator. I'd say that like name2 is, for example, I have right here in a comment, name2 is equal to, if I said name2 is equal to, name1, it won't achieve what I want. What it'll actually do is it'll have the pointer for name2 point at the pointer where name1 is. So if I modified name2 at any point, I would change name1 as well. And so if I want to actually perform what's called a deep copy, I would use the string copy function. And string copy function, again, takes 2 strings. So here I have immediate value for a string, as well as a variable. And so I'm able to copy the string Sunny into the variable name1. So note how in none of these places I really have like a null terminator. I'm not specifying it. And that's because if every time you use like double quotes in C, for a string, it automatically inserts the null terminator. So you shouldn't need to specify that at any point. One important thing about like string copy and I guess primarily string copy is it doesn't check if you have enough memory allocated to name1. So let's say I only had like 3 bytes of memory allocated to name1, and my name plus the null terminator is going to be 6 bytes. What it's going to do is it's going to actually end up either segfaulting, or if you don't have canaries, it's going to end up overwriting some value of memory, and you're going to start getting unpredictable behavior. And so you want to make sure whenever you're using the string copy function that you have enough memory allocated to the C string that you're pointing to before you copy the variable. So yeah, we can print. So then something that you're gonna, and this is a little bit project specific, and you'll see this as you work through the class, is that you're gonna have to depend more and more on working without C++ data structures. For example, vectors tend to be like something that you can manipulate how long they are. And in C++ or in C, there are ways to do that using malloc and free, but they tend to be a little bit more difficult to work with. And so as I was mentioning earlier, sometimes we don't care about how efficient your solutions are in this class. And so when you're not sure, you can allocate more memory than you need. And so, for example, I have this C++ or char container. And in this container, what I wanted to do is I wanted to hold an array of strings. I wanted to hold exactly 3 strings, in fact. But I don't know, at least at this point, how long those strings are going to be. All I know is that they're going to be less than 8 characters, including the null terminator. So what I'm going to go ahead and do is just make it 8 long, regardless of how much memory I'm going to need. And so if I look at my string copy here, even though hello technically only takes 6 bytes of memory, I'm gonna put it into the slot for that has 8 bytes of memory. Even though like 2 of those bytes will end up going unused, we don't care about efficiency. And so unlike 281, we're not going to worry about this. But here I have a string EECS, which is going to be 7 characters long plus the null terminator. So it's going to take the entire slot. And so this will become a little bit relevant as you work through some of the projects. So here I am copying each of these words into different slots in the containers, and then I can print them. And so when I print them, what you'll end up noticing is that it will stop at hello. It won't print 8 bytes. It'll only print 6 bytes. And then the reason, 6 bytes. And the reason for that is the null terminator kind of signals to it when to stop, not the amount of memory that's allocated to it. So this should print hello world in EECS. All right. Another difference is in C, there are no booleans. So you guys might have always thought of a boolean taking 1 bit, something that just takes the smallest amount of memory, and because it can only take the value of 0 or 1. In reality, if our computers were to treat booleans as bits, it would be really slow, and we'll talk about that as we go into like architectures. But the way computers tend to work is they grab data in big chunks, and depending on your architecture, generally in bytes. And so if I were to grab a singular byte and pull it into like a register, then I would just be wasting, or I don't need the rest of that data. And so in C, we don't tend to support booleans because they're slow. And so in C, if I wanted something that acted like a boolean, I could just use an integer, and that integer, when I want it to be false per se, I could assign it to 0, and I wanted it to be true, I assign it to 1. And so if you're a little bit confused right now about like what I was talking about with how booleans can be inefficient, I wouldn't worry about it. It might make a little more sense as we go through the class, but yeah, I wouldn't worry too much about that. All right. I think, okay, so that's all I'm going to cover for now. I'm going to take you guys to an example where we're going to try to translate some C++ code into C code, and kind of discuss some of perhaps the pitfalls that people might fall into along the way. And yeah, and so you might have noticed that there was a little bit more code in there, but Mason will be talking about that in just a bit. All right, Mason, do you want to switch over to the slides for the demo?
Yeah, there we are.
Okay, so here we have 2 programs. Off to the left, we have a C++ program, and off to the right, we have, to the best of our ability, the most like literal translation we could do from C++ to C. So I took my strings from the STL and I converted them to char pointers, and I took like my print statements, which is the cout, and I turned that into a printf statement, right? And I tried to do that as literally as possible. And when you're writing your code for the projects, you might find yourself kind of tending to do this. But there's a couple problems with this. And so we're going to explore that a little bit. And yeah, so, we have a warning, it's not going to work. And let's try to think about, why this might not work. All right. So we'll start with talking about the strings. So initially we had hello and jello, and the way strings work is when you assign one string to another on the 3rd line, it performs what I call a deep copy, in the sense that it accesses all the memory that's allocated with the string, and it copies over all of that memory. And so the result is we get the string hello the string jello to have the string hello world. This is going to be a little bit different in C. And so we're going to take a look at what might happen if I did that in C. Well, here, instead of, us performing a deep copy, we're going to perform a shallow copy. And what that's going to mean is that jello is going to point at the same memory that hello is pointing to. And so it's not problematic initially, because if I printed jello and I printed hello, they both say hello world, but it's going to become problematic here on this next line. So in jello, I'm going to, modify the first letter to a J. So I encourage you to take a second at this point to maybe think about how that would result in different behavior than maybe my original program did. All right. Feel free to pause it as we go through this. But what's going to happen is, yes, while the string jello is going to become jello world, the string hello is also going to become jello world. So when I print it on that last line, my result is going to become jello world, instead of what the original program printed, which was hello world and jello world. So this is an example of some of the differences, the core differences between C and C++ strings. And so let's think about maybe the way that we could revise this program to have it result in the same behavior that C did. And so the function that we use, and I discussed this briefly earlier, was string copy. And so string copy performs the deep copy that generally C++ strings do. And so in string copy, I just specify the pointers to both of the char pointers. And you might think that this looks good, right? Now I'm performing a deep copy. There's unfortunately still one problem. And so I briefly mentioned this earlier. So I encourage you to pause the video now and think about it for a minute. But the reason, the behavior that we're going to get from this is we're going to get a segfault. And the reason for that is we're going to be accessing unallocated memory. Right now, the char pointer Jello doesn't have any memory associated with it. And so when I try to copy the string hello world into it, it just puts it in a random location or whatever char pointer was initialized to. And that can cause segfault or unexpected behavior. And so the way we allocate memory to the string beforehand is we set up a character array, similar to an integer array, anything that you might have set up before. And the amount of space that I want to assign to it is the length of the string. So using strlength does not include the null terminator. When you use strlen, does not include it. So strlen is going to be 11 in this case. But because I need in terms of the amount of memory that I have to allocate, I still need to allocate room for the null terminator. So I have to add an extra byte to store that null terminator. An alternative to this is you could use the size of operator. And that's the actual the amount of space that's stored in memory. And so I wouldn't have to add that extra byte for the null terminator. So it might be like, if you were doing this, it might be a little bit of a safer option to use size of, but for to make a point, we decided to include using strling. All right, so now the string copy is going to perform correctly and we can move forward. All right, so again, I mentioned this earlier when we were talking about translating between C and C++, but what's the fundamental difference between a struct or a C string and a character array is that they just have a null terminator at the end, right? Well, that might, while it might seem like they're the exact same thing, there's going to be some fundamental differences in the way that you use them. For example, here I have these two structs called double strip, and off the left I have like an idea where I declared two char pointers. I want to have these two C strings associated with a struct, and whenever I access those members, I want to access the strings. So this could be problematic. And the reason that is because character pointers are, what they sound like. They're pointers. They point to different places in memory. And so if my first struct has, if I instantiate my first struct one time and I assign something to, or I use like string copy on that array, it's going to, copy a certain number of values into it. But is not going to actually store the string within the struct. So if I were to look at the size, for instance, of this struct, the size of the struct is going to be the size of two pointers. On the other hand, we have two character arrays where we allocate 8 bytes of memory. And so the size of this struct is going to be 16. It's going to be 8 bytes for the first C string and 8 bytes for the second C string. And the benefits of doing something like this is that if I were ever trying to like copy a struct, if I were to copy my first struct, I would end up copying the pointers. And so similar to the behavior we saw earlier where we'd modify one struct and it would change, or modify one string and it would change the other, we'd see very similar behavior. So, but if I wanted to like copy the second struct with my, allocated memory with my character arrays, it would be a full like 16 byte copy. And so my strings would change. And so this is something you should think about as you're going through your projects, is maybe I don't necessarily want pointers within my structs because I'm not going to be allocating space within the structure. I'm going to be just have pointers to somewhere pointing outside of the structure. And so, yeah. So I mentioned printf and fprintf earlier. So fprintf is just a file printf. It acts the exact same way, except you can point it to a file stream. And so, yep, here's a bunch of type specifiers. So the ones that are those are gonna be the ones that are relevant. There's actually a couple others. And so if you really are interested, you can go and look on the C documentation, and they actually have a ton of type specifiers, but those are gonna be the ones that you're primarily gonna be using for this project, or any of the projects in this class. So I've shown you examples of this, so you should be familiar with this already.
Yeah, there is one really important caveat in this slide, I think. We see a lot of like people trying to print out a number, right? And they'll just do like printf, and then the only argument will be like the number, but that wouldn't work. So printf, that F in printf stands for formatted string. So we always have to give it a string as the first argument. So make sure you always include a string as the first thing in your printf arguments.
Absolutely, great point. So now, as you're going through your code, and I mentioned this briefly earlier, you might run into a couple problems. You might start segfaulting randomly, or you might start getting really weird values. And so a heavy suggestion that I'm giving to you now, I know there's going to be a lot of students who don't listen to me now and run into problems, and they're going to figure out workarounds, and they're going to look at their code long enough, and they're going to figure it out. But what I suggest is using some form of a debugger. The officially supported debugger for like staff, if you went to like office hours, most of our staff is at least somewhat familiar with using command line GDB. It's called GDB because it's the GNU debugger. The way it works is it allows you to set the primary use for it within the scope of this class is it allows you to set breakpoints. And what that allows you to do is stop your code like part of the way for it through it running, and look at maybe what the values of certain variables are, and then you can look through those values, and maybe one of those values is not what you expect it to be, and then you can go look back and take a closer look at a particular piece of code instead of just running your entire code and just seeing a seg fault and being super confused as to what's happening. There's still a couple other ways of debugging. So you can use assert statements. If you want to use assert statements, you have to include the library cassert. And once you do that, if you type assert around type assert and then parentheses, and then you put any statement that would evaluate to a Boolean in there, it ensures that it'll be true. So if I did assert true, that would pass every time. But if I did assert false, it'll stop my program exactly where that is, and it'll also tell me where it stopped, right? And so that'll give you a good idea of maybe if I wanted to make sure that something was following a behavior, like a value was between a certain range, I could write in assert statements checking if something was less than something, and then if for whatever reason it was outside of that value, it would stop the program there and tell me where it stopped. And so it's also a very useful tool. You can also use printf, which I'm sure you guys have used or at least see out that you guys have used in the past. And again, a good suggestion if you're really struggling with a bug to hop in and maybe learn how to use GDB. And so there's a couple of tutorials if you're really curious on how to do that. We have them linked. Again, 280 also teaches you how to use a couple visual debuggers. And so visual debuggers are really just GDB or LLDB or a couple other debuggers under the hood, but they are nice because they provide a nicer visualization of what's happening. And if you're unfamiliar with some of the commands for GDB, it can be a bit much for the first time you're using it. So I welcome you to try those out if you're using VS Code or Visual Studio or Xcode. They're pretty useful. Yeah, I think that's all I have. I'm going to hand it off back to Mason. He's going to talk about how we represent numbers and just different types of numbers in C and just all computers. Yeah.
Yeah, thanks, Sunny. That was a really thorough tutorial, and I think that will really help on the projects. So we're going to get sort of into more of what is actual course content. So the C stuff, like I said, is going to be used for the projects, but EECS 370 is a very conceptual class compared to others like 280 or 281. So we're going to get into just the basics for now, which is numbers. So computers are built on numbers. We use numbers all the time in our code, but we don't often think about how numbers are actually stored in our computer. So we'll just get into that. So to start off with a couple definitions, we're going to use a couple different number systems in EECS 370. And we have decimal, which is just the basic human number system, 1, 2, 3, 4, 5, and so on, your regular numbers that you use in math. But our computers are going to represent numbers in binary instead. So binary is a number system with only 2 digits. So it has 0 and 1. And we use binary in computers because it's the least number of digits in any number system. So if we had 1 digit, that would just be the number 0, and we couldn't represent any other numbers besides 0. We can't use like 0 numbers, obviously, because that means we wouldn't have a number system. But in a binary, we have 2 digits, and we can still represent every regular decimal number in binary. But on our computers, pretty much everything on your computer you can think of as a light switch, on and off, low voltage and high voltage, or true and false, or something like that. And so our computers just have tons and tons of these switches, and they're all made out of different things. But each one of those is going to represent one of these 0 or 1 digits, which we will call bits. So it's like digit, but bit, same thing. And then in EECS 370, we do have one more system that we'll use, which is hexadecimal. Hexadecimal is a number system with 16 digits. And so we'll see what that looks like. And then we might at some point mention like quartic or octal, but we'll look at that as we go on here. So this table gives us the basics on each of the 3 number systems that we'll be using. And so the base of a number system is going to tell us place values, which we'll get to in a second, as well as the number of digits that we have. So if we're in decimal, that prefix decim means 10. So we'll have 10 digits, and everything is going to be based on powers of 10. For binary, it's going to be 2, and for hexadecimal, it will be 16. So hexadecimal, we will add the letters A through F to represent the numbers 10 through 15, but we'll still treat them as regular single-digit numbers when it comes to hex. So we have this example, and I'll have you just trust me for now. This is the number 94, regular number 94, and we would take this exact same number 94, and we can represent the same value in binary and hex with completely different digits. And we'll break down in a second how we would convert between the two to represent the same value. And luckily for us, all of these are going to be usable in C and C++. So for regular decimal numbers, do what you've been doing in EECS 280 and just type them in. But for binary numbers, we're going to use a 0b prefix, as you can see on the right here. And then for hex, we'll use the 0x prefix to declare these numbers. But if we were to look in the debugger that Sunny showed us and look at the value of x after declaring it in any of these 3 ways, we would all see 94 because these 3 representations have the same value, right? And so to get a sense of how we can convert between these values, we're going to look at expanded form. This is something that my school did in elementary school. I don't know if yours did, but we'll go over it real quick. So when we have any regular decimal number, we can write it out in expanded form. So we take every digit and multiply it pretty much by how much it's worth. So in this example, we have this number 913. So, like I said, it's 900. So we will multiply 9 times 100, and the 1 times the 10, and the 3 times the 1. And those 2 statements are equivalent. So notice how we're multiplying by things like 100 and 10 and 1. Those are all powers of 10. And if we were to keep adding digits to the left of the 9 in our 913, we would continue to multiply those digits by a place value that is a power of 10. So, 1,000, 10,000, 100,000, and so on and so on. Even when we think about going to the right of the 3, for decimal numbers or something, we would be multiplying our digits by powers of 10. It's just the exponents would be negative. So we'd have tenths, which is 10 to the power of -1. We'd have hundredths and thousandths and so on and so on. One other thing for notation, we're going to call, well, we're going to number the digits. Besides their digits, I guess, we're going to number the place values also. So the 9 in this example, because we're multiplying 9 times 10 to the power of 2, we're going to call this digit number 2. Similarly, the 3 here would be digit 0, and the 1 would be digit 1. And so we're going to get into our binary numbers, and we're going to be referring to bits the same way, counting up from the right to number all of our bits. So we can do the same type of expanded form in binary and hexadecimal. The steps are the same. We break up all of our digits, which in binary will be bits, or hex will be hex digits. We get all of our place values, and then we'll multiply them together and sum them up to get our values. So we're taking the example that we had before. I said, just trust me. And here's the proof. So we'll start with the binary. So the binary, we've lined up all of our bits with our powers of 2. And notice down here, when we do the expanded form for 94, we'll explicitly multiply the digit by its place value. But since our binary digits are just 0 and 1, we can either include the place value or we just remove it. So we aren't multiplying 1 times 2 to the 6. We're just putting in 2 to the 6. Then we're not including 2 to the power of 5 because 2 to the power of 5 times 0 is 0. So if we take 1 times 2 to the power of 6, 0 times 2 to the power of 5, and so on, we will eventually get 94. And the same thing is going to be done for hex. We'll take our hex digits and multiply them by their place values to get our sum. So here our powers are 16. And one thing to notice is that the rightmost digit or bit or hex digit is always going to have a place value of 1, since anything to the power of 0 is going to be 1, except for like 0 to the power of 0, or any positive integer to the power of 0 is going to be 1. So we will always have a ones place, but then everything else will have different sizes. So here in this example, we're multiplying 5 times 16 plus e, which is 14 in the new digits that we've added. And we're taking e times 1, which is 16 to the power of 0, and summing it up to get 94. So now if you have a binary hex number, you will know what the value would be in decimal. So each week, these discussions are going to have little problems that we can go along with. And so I'm going to go through this one real quick, if I can get my pen together. So we have this binary number, and now we kind of want to go the other way first. And so we want to convert this into decimal. And so this is going to be a lot of sums. I'm going to go from right to left. So we have 2 to the power of 0 plus 2 to the power of 2 plus 2 to the power of 3. And then we have, what is that, 2 to the power of 5, 2 to the power of 7, 2 to the power of 8, and 2 to the power of 10. And I'm not going to sum that all up in my head, so I'll just pull up the answer here. That all comes out to 1,453. Now, there is a much easier way to do this for hex, and that's to not multiply everything explicitly in binary, but we can convert much easier between binary and hex because 16 is a power of 2. So explicitly 16 is 2 to the power of 4. That means that every 4 bits will correspond to exactly 1 hex digit. And so similar if we were to use like a base 8 system, so 8 is equivalent to 2 to the power of 3. So in that case, every 3 bits would correspond to exactly 1 octal digit. And if we were to use something like base 4, every 2 bits would correspond to exactly 1 digit in quartic. But this will make things really easy for us since we don't have to multiply by these really large powers of 16. We can just translate directly. So here we've done that. So we're going to take each section of 4 and we're going to do the powers for those. So this one is 0, 1, 0, 1, which is 2 to the power of 0 plus 2 to the power of 2. That's 4 plus 1, which is 5. And so that's how we get this 5 number down here. We'll do the same thing. So this is 2 to the power 3 plus 2 to the power 1. So that's 8 plus 2, which is 10. And A is 10 in hex. And then finally, we'll do the same thing for this last part. And we got 2 to the power 3, which is 8 plus 4 plus 1, which comes out to 13. And 13 is hex for D. So then we can just concatenate these new hex digits that we got, put them all together, and we get 5AD. And so that makes things really, really easy. And I recommend getting very, very good at doing the binary to hex and back and forth really quickly, because you can just look at a hex number and know generally what the binary will look like without having to get out your calculator at all. So that's problem 1.
One thing I'll note is that you're going to be working with decimal or not decimal, binary and hex a lot throughout this class. So you're going to get a lot of practice. And so, as we work through these problems, Mason's going to sit there and just pull these numbers out of his head. He's going to know what 2 to the 10th is off the top of his head. And to some of you, that might seem like crazy, but as we work through this class, you're going to get really familiar with these number systems and translating that to and fro. And so, if it's not clicking immediately, just keep trying to do a couple example problems and it'll click eventually.
Yeah, for sure. Yeah, I think it might also be helpful to just memorize the powers of 2. So we start off with 1. I think we're missing 2 to the power 1 here, but that's 2. Then 4, 8, 16, 32, 64, 128, 256, 512, and 1024. And then we kind of don't worry about the ones after 1024. And that's because we can associate the 10 really easily with something that's about 1,000. But if you can memorize those powers of 2, it'll make these binary to decimal conversions really, really easy. All right. So like I said before, we can use all these representations and see, here's just another example of that. We did 94 before, but if we wanted to put in the number 15 into 3 different variables in C, we could do it in any of these 3 ways. So 15 in binary is 1, 1, 1, 1. So that's 1 plus 2 plus 4 plus 8, which sums up to 15. And then in F is the hex digit for 15. So all these, like I said earlier, if we were to look at the debugger and click on A, B, and C, we would see that they all have the value of 15. There is also a way to make the computer display something like hex to us. With our printf statements, we can change the %d to a %x, and it'll print out the value in hex. I highly recommend using that in project 1A, because on this problem, we saw that you can convert between hex and binary really, really quickly. And in project 1A, we're going to have numbers that mean more to us in binary than they do decimal, but we're still going to print them out in decimal. So if you can temporarily debug with hex and convert to binary really quickly, that will help you debug a whole lot. All right, so moving on. So in binary, we have addition, just like in decimal. So it's pretty easy to do by hand, just like with decimal. So like, for example, in decimal, if we were to add 37 with 65, we're going to line up the digits with their place values. So 7 and 5 each have a place value of 1, 3 and 6 each have a place value of 10, and then we'll just add them straight across. So we'll start with the 7 and 5. 7 plus 5 is 12, but that's greater than 10. We can't fit 12 into 1 digit in decimal. So we're going to carry the 1 to the tens place. And then we're going to add the carried 1 with the digits that we already have in the tens place. Here we have 1 plus 3, that's 4, plus 6, that's 10. And then we would put the 0 down and carry the 1 again. There's nothing to add the 1 with, so we'll just carry the 1 straight over. And then we would get 102. Same thing with binary, except because we only have 2 digits, we're going to be carrying 1s pretty much all the time. So looking at this example, so if we add 1 and 1, that's 2. 2 in binary equals 1, 0. So we have to carry this 1 to the 2's place and then add it with the existing bits. So 1 plus 0 plus 1, that's 2 again. So we have to carry the 1 yet again. And then we finally get a break here. We add 1 plus 0 plus 0. That's just 1. And we don't have to carry anymore. And then 1 plus 0 is 1. 0 plus 0 is 0. And once again, 1 plus 1 is 2. We'll carry the 1 and we'll put in our 1. And this would be our final answer. I don't even know off the top of my head what the decimal value for that is. It doesn't matter because we can just do the addition straight up. There is one other thing to notice. Notice how when I pasted in these binary numbers, I included some leading zeros. That wasn't strictly necessary, but because our computers are always going to have these fixed sizes for our numbers, we're going to have a lot of leading zeros. So just like how in decimal, if you were to add a 0 in front of the 37, that is equivalent to 37. So just adding zeros to the front is the exact same thing. So keep that in mind.
Yeah, and one thing I'd add is the example that we have for the binary addition here doesn't really have one example of like a binary operation, which is where like you'd have a carry bit, like you'd be carrying a 1 and you'd have them both as 1s. In which situation it's kind of like the way I think of it is like 3. The way I think of a 3 is I keep 1 and I carry the 2, right? It becomes a 1. But it's I'd say it's the least intuitive of them. And so if you ever have a situation, for instance, let me see if I can annotate this really quick. Yeah, if I had like a 0, 1, 1, and I was adding another 0, 1, 1 to it, you know, I get a 0 on the least significant bit and I'd carry my 1, and it would be kind of confusing here. But what we're going to do is we're going to have a 1 and we're going to carry a 1 as well. And we'll talk about that a little bit when we talk about like how they're implemented in hardware. We're gonna have an EECS 270 review at some point. And so we'll talk about like why that is and how that gets represented in hardware later. But it's something to note if you're a little bit confused about what happens when you run into that situation.
Yeah, thanks. I think it's really funny that you pull up that example where you're adding a number to itself. So I'll just write it again. So in decimal, if you add a number to itself, you multiply that number by 2, right? And so it's the exact same thing in binary. If we take a number and add it to itself, so here we would get 1, carry the 1, 1, carry the 1, 1, and then I'm just going to add a 0 to make things clear. Notice that the 0, 1, 1 will show up in our final answer, except with an extra 0 at the end. Also similar to, let's say that we were to multiply 37 times 10. Well, that's just adding a 0 to the end, and we would get 370. In binary, when you multiply a number by 2, you just add a 0 to the end. So that means that when you add a number to itself, you just add a 0 to the end. And that's because 2 in binaries are base. This right here, 10 in decimal, that's our base. So that's what makes the bases really important, those adding zeros. All right. We're going to get into, well, like I said, in Project 1A, the binary values are going to be more important to us than the decimal values. And you might be confused as to why, because aren't they all the same thing? We're going to see when they don't really mean the same thing. And so we're going to call this bit manipulation in C. There is a video review that we have, but we'll go over everything here also, and specifically all the operators that you'll need to know for the projects. Right. So I just showed an example where we added a number to itself and we got a 0 at the end. So that was the same as multiplying by 2. So we're going to call these adding zeros to the end, we're going to call that a left shift. So this example down here, that's a left shift. And we're going to use this little left operator, 2 left arrows, and that will shift. And then the number after the operator is how many zeros we're going to add to it. So if we have this number A, which is 18, you'll have to trust me that this is the binary representation of 18. If we left shift it by 2, that's just adding 2 zeros to the end, and then we get whatever that is in binary. So when we left shifted by 1, just adding 1 0, that was the same as multiplying by 2. So that trend is going to hold for all left shifts. If we multiply by some number, in this case 2, that's equivalent to multiplying by 2 to the power of that number. So if we were left shifting by, let's say 3 instead, that would be like taking our original number and multiplying it by 2 to the power of 3. So we can do some quick and easy multiplication with powers of 2 specifically if we do left shifts. Right shifts are going to be the same thing except reverse. And the only tricky thing about right shifts is that we have the potential to cut off numbers. So when we right shift here, we're cutting off the last 2 digits and shifting everything. So these are going to get cut off. We lose a little bit of precision, but that's going to be okay. And so if left shift was multiplying by a power of 2, right shift is either dividing by a power of 2 or multiplying by 2 to the power of a negative number. So if we have, again, 18 and right shifted by 2, it's going to be an integer division by 2 to the power of 2, which is 4. So 18 divided by 4, that comes out to what, 4.5. But since we're keeping this in an integer and not a float, we're going to do the integer divide. And in C, C++, you might remember this, integer division just removes the remainder, the decimal point. So if you have something that's already a multiple of whatever you're dividing by, you'll get the exact answer, but otherwise it'll take the floor of the number, the actual mathematical answer. So yeah.
I do want to add one thing. So as Mason brought up, in right shifts, we can have like kind of these bits fall off the end, right? And the term that you'll often hear associated with that is truncation, right? And so, you know, we have our 8 divided by 4 turn into 4 instead of 4.5. Well, often when it comes to representing numbers, we allocate, or we say we're only going to represent our number in this many zeros and ones, right? And so say I only allocated 32 of these zeros and ones. And so what happens when I left shift? And if, let's say I had a 1 super far out on the left, it was a really, really big number, right? Well, if I left shift, we kind of see the exact same effect that we're seeing for right shift, where the numbers fall off the end on the left side. And there's actually 2 ways of treating that. And Mason will talk about this later. But just like we saw truncation here, we can have potentially truncation on the other side. You'll see within like computer languages like C and C++, they handle them a little bit differently. But you could, by the definition of like the theoretical definition of just a left shift, you could have the bits fall off on the left side as well. So it just kind of depends on how long your integer is, or whatever your binary representation is.
Yeah, that's a good point. All right. So we'll move on here. So we have a couple other operators that we'll go over. So first we'll have the bitwise and. So in C++, you probably used the double ampersand, like this, to do like if statements. So if this is true and this other thing is true, then do this. So bitwise and is going to be a little different from logical and, but we're going to do the truth table from 270 or 203 on every single bit in the 2 numbers that we're anding together. So here we have this example. We have 26 and 15. We've written this out in binary so that we can see what's going on here. So when we do an and between A and B, we're going to look at this truth table and we're going to go bit by bit, just like with our addition from a minute ago, and do the operation. So 0 and 1, looking at our truth table, that's 0. So we'll put that 0 there. 1 and 1 is 1. So we'll put that 1 there. Conveniently for ands, if you see a 0 at all, your answer is going to be 0. So here we see a 0. I don't even care what this other thing is. I put in a 0. But here we have 2 1s, and so we'll put a 1. That means that if you have a sequence of multiple zeros, you don't even have to look at what the other thing is. You know that they're just going to turn into zeros. And so that's what we've done here. And that was that left side truncation that Sunny was talking about. So if you have a string of zeros on the left side, it will reset your final answer to a bunch of zeros. On the other hand, if you have a string of ones, it'll take whatever was in the other thing and just copy it down. So we have this 1010 that we've copied straight down to our final answer. So we're going to be using this in project, let's see, I guess 1A and 1S a lot, and even 1M, all of project 1. Actually, every single project is going to be using these operators. So we're going to call this process of resetting a bunch of bits and copying all the others, we're going to call this masking. So in this case, B, we could call B our mask, because we're going to copy all these bits from A and zero out the rest. So A is sort of our thing that we're modifying. One thing that's useful for project 4, and you might find it useful earlier, is that just like the left shifts and the right shifts have some multiplication or division relation to powers of 2, our AND operations are going to have similar meanings to powers of 2. So if we have some mask that is a power of 2 minus 1, when we take a number A and we mask it with this mask, that's 2 to the power of, or a power of 2 minus 1, that's the same thing as taking the modulus of A with that power of 2. So we have this additional minus 1 that we have to consider when we're doing our AND operation. It's like, for example, if we look at B, which here is 15, 15 is 2 to the power of 4 minus 1. So that's going to be the same as doing 26 modulus 16, which is 2 to the power of 4. And so that's going to get us a remainder of 10, just off the top of my head. Looking at our final answer, 1010 in binary is in fact 10 in decimal. So we know that this works. That'll be really, really, really helpful on project 4 if you can figure out what that means. And then we also have a bitwise OR operation. Same thing from the AND. We're going to take the truth table, except this time, anytime we see a 1, our final bit is going to be a 1. And if we see 2 zeros, it'll be a 0. So doing the bitwise here, so 0 or 0 is 0. And thinking back to 280 or 203 or 270, remember that 0 is equivalent to false and 1 is equivalent to true. So that's where where these truth tables come from. So 1 or 0 is 1. We have a bunch of 1s here, here, here. So we'll copy them down here. We have 2 zeros, so that would get us 0. There's a 1, and then our finals will be all zeros. So that will be our final answer. Sometimes doing an OR operation will have the same effect as addition, and it looks like in this case it has. If you're adding, I guess, numbers that have no instances of 1 or 1 in the same bit place value, then it'll be the same as addition. So you can use that in project 1 up. But we will, like we called the process with the AND operation, we call that masking. We're going to call this setting bits. So setting bits, no matter what it was before, it turns it into a 1 without changing the other values. So here, our B number is 4. So 4 is just 2 to the power of 2. So we're going to be setting bit 2 of whatever this original number was to 2, or to 1 rather. And everything else is going to be left the same. So 0, 0, 1, 0, we copied that straight down. The 1 here, we copied straight down. The 1, 0 here, we copied that straight down. And so the only thing that we changed was this 1 bit that we set in the 4's place. All right. So let's do an example. So we're going to do a little bit of C code once again. So they're asking us to set bits 7 through 4, which are these bits here, to be 1011 without changing any of the other bits. So we want these to be 1011. Now, the first thing we might think about doing, we might take A and do an OR operation with 0B1011. But if we were to do that, that would not put 1011 into the place that we want. That would put 1011 into the rightmost bits. And so if I get my pen back here, that would put it right here. And our final answer would be this. And we wouldn't have changed the actual bits that we want to. So instead, what we're going to do, we're going to left shift this number by 4 places. And when we do that, we'll get it lined up properly. So we'll have our 4 zeros, since we're left shifting by 4. There's our 1011. And we will have the 1011 0000. So doing the left shift by 4. And I'm going to put these in parentheses for now, since I don't remember my order of operations always. And that will get us the value that we want to for A. Once again, I don't even know what the actual decimal value is. I don't really care, because we have modified these 4 bits to be what we want them to be. Yeah, so there's the same thing. Yeah, there's a couple different ways to do things quicker. So you can just do the straight up the or equals. So like in C++, we had plus equals, which will just add the number to itself and store it back in that same value. Similarly, we have the or equals down here. That's problem 2. Now for problem 3, we're going to mask bits instead. And so mask, that's a sort of a synonym for extract. So if we want to extract bits 7 through 4, which again are these, we're going to make a mask. And whenever we're making a mask, we want to ask, what do we want to preserve and what do we want to get rid of? So whatever we want to preserve, we'll put 1s in our mask. So we want to preserve these 4 bits here. So put 1s there. And then everything else will have 0s, because we want to get rid of it all. So we'll do our AND operation like that. So we have A and I'll do shorthand again. I'll just do 1111 left shifted by 4. But when we do this AND operation, so our final result will be 0010, but we'll still have these trailing zeros at the end, and this will all be 0. So we'll now have to shift it to the right in order to isolate or extract just these 4 bits. So now we'll take this result and right shift it by 4. And I'll put parentheses around the whole thing. And so notice how the 4 that we shifted by here is the exact same 4 that we're going to right shift by for our final answer. So here they've done the same thing in more lines. And so our final result would be 0010. So we just went over the bitwise operators. We can still use the logical operators in C for our if statements or while statements or for loops, but don't confuse the two. So know that these on the right side are bitwise, and these on the left side are logicals. We also have a bitwise XOR, and our logical XOR, I think, is a double caret. That might only be in Verilog, but you shouldn't really need to know that for this class. Yeah. All right. But yeah, we can use it in C, just don't confuse them. And I'll show you why. We have this code here. We want to print out it works. So we have this number 2. So if the number is not 0, but it's less than 3, and 2 definitely qualifies because 2 is not 0 and 2 is less than 3, we want to print that it works. But this isn't guaranteed to work. So if we take I, that's 2, and 2 in binary is 1, 0. I'll add some leading zeros. And then I less than 3, well, that's a logical. And even though we don't have booleans in C, that number is going to be stored somewhere. So that could be 0001. It could be stored as a bunch of ones. We don't really know because it's a Boolean. It's dependent on the system. So when we do a bitwise operation between these two, this is going to come out to 0000 because the 1 and 0 is 0 and 0 and 1 is 0. And so we will never go and print this line, even though we wanted to. So if we were to fix this, all that we would have to do is add an extra ampersand, and that would fix it. But be careful about that. And definitely don't mismatch them. Even if it works on your computer, it might not work on Cane or the autograder. Right. I said that I'm really bad at remembering my order of operations, but here's a handy list. You can also click the link to get the full list. But these are pretty much everything that we'll use in 370. So things like unaries, which unary means one argument, those will be evaluated first. And then we just sort of do our regular PEMDAS. We'll have multiplication, division coming before addition and subtraction. And even though our shifts and our bitwise operators have analogs to multiplication and division, they're still going to have less priority. So just make sure that you know the order operations. And if you're like me, just use parentheses everywhere so that you know explicitly what's going on. Because I'll tell you, like when you go to office hours, and if you have a bunch of weird order of operations, I wouldn't say that the eyes would know without looking up the documentation what the order is, and that just wastes time. So yeah, be really clear with your order of operations and your parentheses. All right. Finally, we're going to get into negative numbers here. So in binary, we've covered positive numbers so far, how to convert from decimal to binary with positive numbers. But in binary, since everything's a bunch of light switches, we can't just add a negative sign to the front of a binary number. Like this is not -1 because we have no way to represent this negative sign in binary. So we're going to have a couple different schemes in the computer world to deal with that. Sometimes we'll just add a bit at the front. So we'll say if the bit is 0, then it's positive, and if it's 1, then it's negative. And we're going to call that signed magnitude representation. There's this other thing called 1's complement, but we're going to use 2's complement because that's generally the standard on computer systems. So 2's complement isn't just for negative numbers. We can still represent positive numbers in 2's complement. And so 2's complement is just going to have a slight modification to that expanded form that we were looking at earlier. So you'll recognize this from a couple slides. The expanded form, we're multiplying the bits by their corresponding power of 2. But this time, we're going to take the leftmost bit. It's going to have the same magnitude of place value, but we'll give it a negative place value. In this example, we have 0011, which in regular binary was 3, because it's 1 plus 2, which is 3. And in 2's complement, it's going to have the same value. But if we were to overwrite this 0 with a 1, we would suddenly add -2 to the power of 3, which is 8. And then let's see, so -8 plus 2 plus 1 is -5. So that's how we would do an example in 2's complement. So I said that the leftmost bit is going to have a negative place value. And so we'll also call that the most significant bit because no matter what, the magnitude of the place value, here it's 2 to the power of 3, is going to be greater than the magnitudes of all the other place values. If that weren't the case, then we would still only ever have positive numbers, which we don't want. There's a couple cool things that we can do with 2's complement compared to the other ways of representing negative numbers. We can get from a negative binary number to a positive binary number really, really quickly. And to do that, we just flip the bits and add 1. So if we have 3, which is 0011, we invert. That's doing a bitwise not in C. So we change all the 0s to 1s and all the 1s to 0s. That's 1, 1, 0, 0. So that's negative 2 to the power 3 plus 2 to the power 2. So that's negative 4. And then if we add 1 to negative 4, we get negative 3. And you can see the expanded form for negative 3 up here as an example again. Negative 2 to the power of 8, or sorry, negative 8 plus 4 plus 1 is going to get us to negative 3. So that's the really easy trick. That's why we use choose complement. So for example, let's say that we're trying to write 16, or rather negative 16 as an 8-bit 2's complement binary number. We have the binary value for 16. So we're just going to flip it 1, 1, 1, 0, 1, 1, 1, 1, and add 1. So I'm going to add 1. And here's where knowing how to do the binary addition is really helpful, because I don't really have to calculate this. So we have 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, carry the 1. And there's nothing else to carry, so I'll just copy down these numbers. And notice how that most significant bit in the end is still a 1, which means that this is a negative number. So this is negative 16. Yeah.
Just going back really quickly to like why we represent things in 2's complement as opposed to maybe another system. So something that might be a little bit more intuitive, some of you might be sitting there asking, like, why don't we just have that most significant bit, that bit the most to the left, just represent the negative sign, right? So 3 would be the same as negative 3, except that last bit would just be, is there a negative sign or is there not? And the reason for that, and Mason, you might be going into this next, but I'm not sure if it's on the slides, but is representing it that way allows us to maintain our form of addition as well as like subtraction. What it allows us to do is, oh, it looks like Mason has it right here, is to represent the numbers in a way that we can represent them as negative, while converting really quickly, while also allowing us to add. So I'll let you pick it up from here, Mason.
Yeah, no, that's entirely true. 2's complement, that addition that we do by hand, where we line it up, we carry the ones, all that, it's going to be the exact same. We have to remember about our overflows if we go out of range of whatever number size that we have, but otherwise it's going to be the exact same. And that will be really helpful, I think, in a lot of the projects, recognizing that. So for example, if we have 8 plus 4, which is 12, so we could line up our bits here. So let's see, that's 8. This is 4. When we add it up, we get that, which is 12 in unsigned numbers. So unsigned meaning no 2's complement. But if we do the same thing, it'll work out the same. So if we're doing the same thing, so now these, this column here is negative. So this is equivalent to negative 8, and this is equivalent to 4. When we add them together, we get negative 2 to the power 3 plus 2 to the power of 2. So negative 8 plus 4, that's negative 4, which all works out. And then this thing down here with the negative 1 and the 2 to the power of 16, that's just an example of overflow. In unsigned numbers, if we were to add 1 to 65,535, which is all ones in 16-bit numbers, we would add the 1, and then all of these would turn to 0, and we'd carry the 1, but we'd have no place to put it, so we'd truncate it, and then that number would be 0. But here, if we add 1 to negative 1, it would come out to 0. So it would be doing what we want. So we have to pay attention to the overflow here. But yeah, this is really important for 2's complement. One of the reasons that we would want to use 2's complement over something like sign magnitude is because whenever we have a finite number of bits, like let's say that we're working with 8-bit numbers, we want to represent as many numbers as possible. We don't want any wasted space. So with 2's complement, with 8 bits, we can represent exactly 2 to the power of 8 numbers, distinct numbers. They're all different. They don't have the same value. But with something like sign magnitude, we could do like this 8-bit number, that's negative 0, right? And here is positive 0. And since -0 and +0 are the same thing, we're kind of wasting space for one of the numbers. So just another example with negating a number in 2's complement. If we have 43 and we want to get -43, we flip the bits. So 0 to 1s, 1s to 0s, and then we just add 1. And so if you don't have a long string of 1s, it's just really easy to add 1 and replace the 0 at the end. So yeah. So yes, so the things to look at for a binary number for 2's complement, if the most significant bit, that leftmost bit is 0, it's positive, or it's 0. And if it's 1, then it's a negative number. Yeah, one nice thing about all number systems is that if you see a bunch of zeros, it's always going to be 0. There's no way it could be something else. So we're going to call it positive for our purposes. Yeah. One last thing is that 2's complement might look different depending on what size of numbers that we're dealing with. So if we have, let me think, -2 in 2's complement for a 4-bit number, that's going to be 1110, right? Because that's -8 plus 4 plus 2. So that's -8 plus 6, which is -2. But if we're doing 8-bit numbers, it's going to look like this. It's going to have these extra 4 1s at the beginning, because now this right here is the negative place value. That's going to have a place value of -2 to the 7, so that's -128, and then we'll add 64. So -128 plus 64 is -64, and then we would add 32. So -64 plus 32 is -32, and so on and so on. And so we're going to call this process sign extension. So whenever you grow a number from a small number of bits to a large number of bits in 2's complement, you take that leftmost bit and you duplicate it all the way down. So like we said before, if it's a 0, if it's a positive number, so this is what, +6, you would just add a bunch of leading zeros because that's the same value. But for negative numbers in 2's complement, we're going to sign extend with a bunch of 1s instead. Yeah. One more cool thing. Let's see, this says try to do the negation of 0 on your own. And I'll go ahead and show you. So if we have 0, which is a bunch of zeros, and we negate it, we'll get a bunch of 1s. And then if we add 1, like we showed in the example before, let's see, that will become a 0, and we carry the 1, and a 0, and we'd carry the 1, and so on and so on. And then we do that, it would overflow, and we get zeros again. So -0 is 0 because of computers. So yeah, so just because of the sign extension, if we want to go the other way from a large negative number to a small negative number, we can just cut off the leading 1s. And you'll want to use that idea in project 1A for sure. Right. So lastly, just a couple of notes. So our computers are going to store everything in binary, even if it looks like decimal or hex to us, it's all going to be binary in our actual computer. So you don't need to do something like, you could, maybe if you wanted to do like an int 32 and then like a bunch of zeros and 1s and all that, that would be a giant waste of time. You'd be so confused. It's much easier to create an int and then use the binary and then print out the decimal value. So yes, so do not do this. Bad. All right. Yeah, and then you also don't have to mess around with a bunch of memory and stuff. You can just use an int. Right. Yeah. And our computers, if you see an int, it'll be in 2's complement. The only time we won't be using 2's complement is if you see the unsigned keyword in C or C++. So an unsigned int is still a 32-bit number, but it's all positive numbers or 0. So it has a range from 0 to 2 to the power 32 minus 1. Yeah. So don't ask about converting between these two different formats, or really any of these formats that we've talked about today. Right. That's all the slides. Sunny, do you want to go over the bonus content from the demo?
asked me to. Yeah, I can go ahead and do that. We'll take a look at like using all these operators that we discussed, as well as just a couple other you know, cool
Yeah.
little things. Leave annotation mode. There we go.
You know, I realize these slides, they said fall 2021. It is not fall 2021 anymore. It is winter 22.
That's a new year. All right. So we left off here, and we were looking at two numbers. So we're going to look at primarily here now, just using binary operators. So here's an example of us trying to, you know, representing a number in binary, and using unsigned or signed ints. It should be the same value regardless in this case. This number evaluates if I wanted to convert to decimal to 6. In fact, VS Code is nice. If I hover over the number, it tells me the value. Great. And so let's say I wanted to perform a bitwise OR on these two. So again, as Mason mentioned, it's just a singular like bar. You guys might have like performed logical ORs throughout you know, your course at 280, or if you have taken 281. And those are going to be 2 bars. And you might have initially thought, like, why the heck do I have to have 2 ands, or why do I have to have 2 ORs? And the reason for that is that C implemented these operators as default binary, and then like if you added another character, it's a different operator. So it's just kind of, I guess, representative of like the development of computers, in the sense that like you know, bitwise operators always took precedence. But just as a gimmick, the way you perform a bitwise OR is as follows. Yeah. And so you can see our value changes to our output's like a 7. So print it at the bottom, give you my result. All right. So then I want to perform a bitwise and. I can do the same thing. It's going to be 1 ampersand. My result is going to be a 4. And so note that these aren't going to be like your logical ands or ors where you'd get like a 0 or a 1 if you printed it. Okay, again, we can do a logical shift, or we can do a bitwise shift. Throughout C and C++, most of the shifts are going to be logical shifts. And the only difference between what we call, you know, a bitwise shift and a logical shift is the way it deals with truncation. So I wouldn't worry too much about that, about the difference. We'll actually go into this a little bit more once we start talking about a couple other assembly languages, but I wouldn't worry about that right now. The way this operator works, this is really, so right here I have an example of us using, you know, a less than sign, a less than sign, and then equals to. This is the exact same. I'm just going to type it here in the comment as binary 1 is equal to binary 1 left shift 2. So basically, the second argument, if you want to phrase it that way, to the operator is how many digits you want to shift your number over, and the first argument is going to be the number that you want to shift over. So it looks like binary 1 right now is a 6, right? So it looks like this in decimal. And so if I want to go ahead and perform the operation, it took the value of 24, and the value of 24 in binary is going to be 0B1100 and then 0. And so I kind of added these last 2 zeros by performing that shift. Right shift is going to work the exact same way. Remember, you have to account for the fact that you might truncate. Maybe sometimes that's what you want, but it's important to remember that the right bits will just kind of get cut off. So if I perform binary 2, so the initial value for binary 2 was 5, and I left shift by 2, I end up getting 1. And the behavior of that is going to be like the same as if I divided by 4. But yeah, I should go ahead and print that. Awesome. So these are just a couple of like C quirks that you might find helpful. You don't need them. In fact, I went throughout the class without really using any of them. And you might want to like reference, if you're really curious, you might want to reference this further on in the course, because, you know, obviously there's probably some of you who don't know what a register is right now. And we'll talk about that a little bit later when we talk about like how processors work. But registers are essentially, so you have multiple types of memory. You have like RAM, which is like what most people refer to as memory. And RAM's, you know, pretty fast. You have disk, which is, you know, a lot slower. And then above that, you have this really, really fast memory that's called a register. And registers are usually what your processor is working with. The way I like to think of it is in terms of like memory is if I had hands, and my hands, they can do things really fast. But my desk has a bunch of tools on it, right? But I can only hold, because I only have two hands, I can only hold so many tools in my hand at a certain time. And so if I wanted to, like, per se, hammer a nail into the wall, I would, you know, pick up my hammer, put it in my hand, and then use the tool. And registers are kind of the same way, in the sense that registers are like my hands, and like all other memory is kind of like my desk. It's a lot slower, and if I want to end up like working with that tool, I have to, you know, pick it up. And we'll talk about this later on. So if, you know, this is confusing to you, I wouldn't worry too much about it. But the way I think of registers is it's just really fast memory that I can work like that I perform all my work with. So in order to use something, it has to be in my hand. And so I might go to my memory, grab it, and put it in a register, and then use it. You know, those registers are really fast memory. And so at times when I'm programming in C, I might want to say, hey, this variable, I need to access it a lot. I need to access it really, really fast. And so I tell the compiler to make sure that when this variable always goes in my register. And so it allows you like a level of control. Under the hood, when you turn your code into machine code, and we'll talk about that later, when you're compiling your C into like another assembly language, it will already create these instructions to manage moving, you know, your variable into and out of registers. And that's something when you're programming in C++ and C, you really don't have to worry about too much. And the reason for that is that compilers are really, really good. Compilers are really, really good at deciding what goes in registers and what doesn't, right? It looks at your program and says, hey, man, this guy's going to use, or this person's going to use the register or this value in memory a lot. So I'm going to keep them in the register. And so compilers are really, really good at it. So you really shouldn't need to do this. In fact, very few programmers will ever use this, considering that compilers are really good now. But back in the day, compilers used to not be nearly as good as they are now. And so, you know, sometimes this was useful. And you'll see, like, if you look at some older languages or some more like hardware-based languages, that they interface and use like registers and manipulate registers a lot more directly. But this is a cool little quirk that C has. Here's another thing. I talked about structs earlier, and if I want to, if we look back at like my struct from earlier, I had 3 members, and the order that I declared them was X, Y, Z. So if I want to initialize, like I want to create an instance of this class, and set all the values all in one line, right? I can put the values in the order that I declared them. And so like X was an integer, and so it takes the value of 370. Y was the character within the scope of the class, and so it takes the value of E, and so forth. But if let's say I'm not too familiar, I'm not comfortable with that notation, a completely viable like alternative is I would just access, I'd create my struct victim later. And then I would access victim.x is equal to 370, and I can do the exact same thing with all the other variables. So you can do either one. This tends to be like a little bit cleaner, or some people tend to like having it on one line, but under the hood, it does the exact same thing or very similar things. The compiler optimizes it out, but yeah. Another thing, I think I ended up bringing this up a little bit earlier, is that you can have like multiple values. So if I want to print, you know, all of the entire struct that has like 3 members, and so I would have to print, have 3 type specifiers and specify each one of them sequentially. Cool. The ternary operator, this is something that I've just seen kind of underutilized perhaps, or just some people aren't sure about the way it works. So what happens a lot is you have like statements like this, and I have like an if a condition, I want to set something to a certain value, and if not the condition, right, if else, I want to assign the thing to a different value, right? And ternary operators are just like a really nice way of doing the same thing, except a lot more concisely. And so the way I represent it, and you're gonna like the first couple times you're gonna use this, you're gonna be like, man, how am I supposed to remember this? But once you use it a couple times, it tends to stick. Basically, the way it works is on the left side, I put like, well, if I were to assign it, right, I would put like the thing that I was assigning to, and on the right side, I first put the condition. I have parentheses here. You don't need parentheses here, but you put the condition, same condition from here in parentheses, and then you put a question mark. And the question mark's what's called the ternary operator. And so the next thing that comes is the value that you want to assign to val if the condition is true. So same as here. So if the condition was true, we assign 3 to the value. And so it'll assign it there. And then you put a colon, and after the colon, you put the value if it were not true. And so the only reason I'm introducing this to you is because like sometimes like code can tend to get a little what I call bloated, in the sense that you just got so many words and so much code in front of you that sometimes it's hard to digest, and sometimes it's kind of just like nicer to squish it down a little bit. And the ternary operator is just like a nice little tool to do that. But in terms of how they work, or in terms of like how fast one would be, they work the exact same way. This just expands into the if statement as far as the compiler is concerned. So it's just a nice little tool that you can use. But yeah, that's all I have. I don't know if you have any other closing statements, Mason, but yeah, that's all. That's all I got.
Thank you for watching. Thank you for listening, and we'll see you for the next one. So.
Absolutely.